This presentation on hydraulic circuits, the 8th in our video training series, provides a comprehensive introduction to hydraulics. Hydraulic circuits, even the most complex ones, are made up from a surprisingly small number of different components. Here on our fluid power trainer, for example, I've set up a circuit that includes a vane-type pump, a relief valve, directional valve, flow control, and cylinder. This type of circuit, with its slow feed forward and rapid return, can be found on any number of machines. I'm Paul Cook for Vickers. Now let's move to a graphic example of another circuit. We'll need a cylinder, a directional valve, and of course a pump and a reservoir for fluid. Filters, too, are a necessity with today's highly efficient components. We placed one at the pump inlet and one in the return line from the directional valve. Now, by shifting the directional valve back and forth, we can make the cylinder piston reciprocate, but we haven't provided a place for the oil to go when the piston stops at each end of the stroke. So we need a form of pressure control. We'll use a relief valve. Now, we'll need something to drive the pump, and that can be anything you select, from an electric motor to a windmill, as long as it can provide the necessary torque and proper drive speed. If this were a circuit for a grinder, we might have a problem. The table would move faster in one direction than in the other because of the differential areas in the cylinder. A simple fix would be to use a double-ended cylinder. Then the speeds and forces would be equal in both directions. Now, there's another way we could get the same results. It's called a regenerative circuit. For equal speeds and forces, a cylinder with a 2-to-1 area ratio is used. That means with the piston retracted, the fluid in the rod end would be 1/2 of what's needed to extend the piston. To make it work, fluid from the rod end, instead of going to tank on the extending stroke, is routed back to the inlet side of the directional valve and from there into the cap end. This means we will have equal pressure on both sides of the piston. But the greater force on the cap end, because of its larger area, will cause it to extend. Since the fluid displaced from the rod end provides half of the fluid required to extend the piston, the pump needs only to supply the other half, and it will only take half as long as it would in a conventional circuit. No, we didn't get something for nothing. Pressure in the rod end resists the forward travel, so what we gained in speed, we lost in force. If it were necessary to regulate the speed of the cylinder piston, this would be a good application for a bleed-off flow control. The workload is fairly constant, and there's no tendency for it to run away. We would save some energy, too, in that the pump would operate at the workload pressure rather than at the relief valve setting. Now, it's often necessary to have 2 cylinders which operate in sequence. That is, one must complete its stroke before the other begins. An example might be a clamping cylinder and a work cylinder. Naturally, we'd have to clamp first, but fluids take the course of least resistance. And if the work cylinder moved easiest, we'd be in trouble. Such an application calls for a sequence valve, which will not only assure that the clamp moves first, but also maintains sufficient pressure to hold the workpiece as the second cylinder approaches. This time we'll use a single directional valve to control both cylinders. The sequence valve, which is held closed by an adjustable spring, will prevent flow to the work cylinder until the clamp is firmly in position. When pressure reaches that required for clamping, it will overcome the sequence valve setting and permit flow into the work cylinder. Pressure in the clamp cylinder will be maintained at the sequence valve setting regardless of how easily the work cylinder moves. However, as pressure in the work cylinder builds up beyond the sequence valve setting, the clamp pressure will also increase. Sometimes, to avoid crushing the workpiece, a pressure-reducing valve is used to limit clamping pressure to a safe maximum. A pressure-reducing valve is held in its normal open position by a spring and is closed by pressure sensed at its outlet port. With the sequence valve and a pressure-reducing valve added to our circuit, we can not only cause one piston to move before another, we can maintain pressure on it between set minimum and maximum levels as the second cylinder performs its function. Now, let's try a rapid traverse and speed circuit. They're quite common in machine tool applications for drilling, tapping, and similar functions. Since the work will be done on the extending stroke, we'll use a long cylinder with a single rod. In order to be able to stop in mid-stroke, we'll need a 3-position directional valve, which is spring-centered with at least the cylinder ports blocked. Next, a large volume pump to provide the speed we'll need in rapid traverse, and the ever-present relief valve. Have you noticed these are the same basic units we used before? This time we'll put a flow control in the exhaust line from the cylinder. A drill might pull ahead as it broke through the work, so a meter in or a bleed-off circuit wouldn't do. We now can control the cylinder speed during its entire extending stroke, but that's not quite what we want. We need to move up to the work quickly, then slow down just before the drill contacts the work. To do this, we'll use a cam-actuated shutoff valve that's normally open. Its proper name is a deceleration valve. We'll place it so it can be closed by a cam on the cylinder rod and pipe it so flow can bypass the flow control during the rapid approach to the work. By properly locating the cam, it will cause the piston to decelerate and feed into the work at the flow control setting. Both flow controls and deceleration valves are available with integral check valves for reverse free flow. But we'll place one here for the sake of clarity. It will bypass both valves for a rapid return stroke. As we mentioned, this circuit is typical of many applications where a large volume of fluid is required at low pressure to move quickly up to the work. Then, only a small volume at high pressure is needed for the work portion of the cycle. With a single pump selected, the bulk of its delivery is not being used during the feed portion of the stroke. As a result, it returns to tank through the relief valve at its setting, and a great deal of energy is wasted. I might not have mentioned this if we didn't have a fix, but luckily we do. It's called an unloading circuit, and it uses 2 pumps, one large and one small. The small one needs only enough volume to supply a little more fluid than our system requires at high pressure. The large pump will help out when the going gets easy, during rapid approach and rapid return. To complete our package, we'll need an unloading valve and a check valve. The 2 pumps, piped together, will replace the single pump and provide the large volume required at low pressure. When the pressure builds up, as it will when we go into the work portion of the cycle, the unloading valve opens, permitting the large pump flow to return freely to the reservoir. The small pump, however, cannot get through the check valve and continues to operate up to the relief valve setting. As the cylinder piston returns at low pressure, the unloading valve closes and the large pump valve again joins the small one for a rapid return. Come to think of it, we not only save energy with this circuit, we can usually get by with a smaller electric motor. With a single pump, the motor has to drive its full volume up to the relief valve setting. Using 2 pumps, the motor drives the combined volume up to the unloading valve setting. The large pump delivery then goes to tank at little or no pressure, and only the small pump goes to the relief valve setting. Now, how about another application? A hydraulic curing press. Here again, we'll need a lot of oil to close the press quickly, then a small amount at high pressure during the curing cycle. Sounds like another good application for an unloading circuit, and it is. But we're going to try another approach, an accumulator. a device for storing oil under pressure. First of all, we're going to need a pump, relief valve, directional valve, and a cylinder. If we select an 8-inch diameter cylinder, it will have an area of 50 square inches, and at 1,000 psi will develop a force of 50,000 pounds or 25 tons. A 15-inch stroke would require 750 cubic inches or 3.25 gallons of oil. So a 20-gallon per minute pump would close it in 10 seconds. We'll use an open center valve, but put a counterbalance valve in the line from the bottom of the cylinder. It does just what the name implies. It counterbalances the weight of the press platen and keeps it from falling. We're able to open and close the press and build up to 25 tons of force. But to hold it for several minutes would have our 20-gallon per minute pump running at 1,000 psi. But most of its delivery going back to tank through the relief valve. And that's not practical. We'd be wasting nearly 15 horsepower. Now, this is where the accumulator comes in. We tee the accumulator off our main supply line between the relief valve and the directional valve. It has a bladder in it, something like the one in a football. Next, we'll pressurize or preload it with dry nitrogen to about 600 psi. This time, when the press is fully closed, instead of going over the relief valve, the oil will start filling the accumulator from the bottom and compressing the gas even more. By sensing the pressure with a pressure switch, we can actuate a small solenoid valve and vent the relief valve when the pressure setting is reached. A vented relief valve opens at very low pressure, permitting the pump to flow freely back to the reservoir. A check valve placed upstream will prevent backflow from the accumulator, and the compressed gas inside will maintain pressure in the rest of the circuit. Any drop in pressure can be sensed by a pressure switch, which at some predetermined minimum pressure will energize a solenoid valve and devent the relief valve. The pump flow will again be directed into the accumulator, but only long enough to replace the fluid lost through leakage, and the cycle will repeat. In this way, the pump will operate under pressure for only a few seconds during the entire curing cycle. Well, looking back, we've discussed a simple reciprocating circuit, a regenerative circuit, a sequencing circuit, a traverse and feed circuit, an unloading circuit, and a hydraulic press circuit using an accumulator. That's 6 circuits in all, each quite different from any other. Now, let's see how many different hydraulic components we used. Reservoirs, common to all circuits, filters, they'll pay for themselves, pumps, the heart of the system, relief valves and pressure-reducing valves for overload protection, directional valves control the motion, cylinders provide the motion, check valves, one-way directional valves, flow controls to regulate the speed, deceleration valves for smooth transition from rapid advance to feed, accumulators for storing oil under pressure, and sequence, counterbalance, and unloading valves. We've grouped the last 3 together because they're essentially the same valve using different controlled pressure sources and either internal or external drain connections. Actually, we've merely scratched the surface of the many possible applications for hydraulic systems. Once we know the motions, speeds, and forces required, it's a simple matter to select the necessary components to provide them. You're probably already thinking up projects of your own. Why not start with a log splitter? You now have the knowledge. Well, that concludes our discussion of hydraulic circuits. In this, the 8th program in our video training series on the basics of hydraulics. I'm Paul Cook for Vickers.